Zachary, can you keep your mask on? Thanks. Yeah, you may need a piece of wire or something in it, or a better shaped one. Okay, let's go ahead and get started. So we were working last time on rotation and general motion. So we had a couple different things we considered. We're going to continue with that today. And then get into a little more with relative motion and acceleration and velocity in systems that are allowed to rotate as well as translate. So that'll be our plan for the day. I'm hoping to leave a little bit of time at the end so we can talk about the exam on Thursday as well. Okay, so for those of you who have not started studying, it would be wise to start studying. Most of the lecture sessions have been recorded, so they are available to you on Teams. So if we go to Teams, and let's see. Share screen. That one. So in our team site, if you go to recorded lectures, they're all right there for you. So you can find, we are missing a few, and I didn't get topics written down on all of them. ahead of time, but most of the lectures are there, so you can go back and watch them if you want to. I think they're all on screen, so I think that'll let you speed it up and go double speed. And you know, there's always gaps where I give you guys time to work on things. So if you can either do that or try and just skip that and keep going. So that may be worth doing with topics that we haven't covered in a while, like friction. It's been a month or so since we've done much with. So that is there. The other piece is that advising day is tomorrow. If you have not yet signed up for an appointment with your advisor, figure out how they are asking you to do so. If you're supposed to be meeting with me, you should have had an email yesterday morning, as well as a couple more last week, with a link to Sign Up Genius to actually sign up for an appointment there. So if none of those times work, let me know. And so those will all be on Zoom. If you're meeting with one of the other faculty members, you should have an email from them somewhere in your inbox. So make sure you know who you're supposed to be signing up with and do that. One of the things you should be doing tonight, if you haven't already, is to come up with a plan for next semester. So figure out what you're supposed to be taking. If you do not know what that is, go to the UNW Engineers page. There's a spring schedule posted along with the recorded advising session from last week. So most of you, I don't think were there, or I don't think attended live, but that's there, and I kind of go through everything that your class should be planning to take next semester. It'll be anything that I say for second years, and then anything that I say for first years that you guys haven't done yet, make sure is in your plan. Okay? Okay. And you know how to get to class schedules and see where things are at. So I've got a summary of what the engineering classes look like next semester, but then it'll be up to you to figure out what else you're taking. So Bible classes, core classes, and when those are and where they fit in. So one thing I will point out, calc-based statistics is on here twice because there are two sections. You and the third years are both taking that next semester. You will need to take the 1125 section because circuits is in conflict with the other one. So make sure that you get that later section time, okay? Unless you're not ready to take circuits, and then you can take, 750 math. So, any questions at this point? Advising, statics and dynamics. Anything else?
Questions about like any materials that we covered so far?
We're not there yet, but anything that is recent. Yes. So we are not yet to the exam review portion of the hour, but if you have other questions, things that are a little more current.
Any updates on cases?
They continue to be high. Yeah, they continue to be, so the historical, I don't know if they have those numbers provided to you or not, but let's see, there's the public dashboard.
And the dashboard gets updated on a weekly basis?
It was a weekly basis. It's actually now, twice a week. So,
Twice a week?
yep. So
I'm not sure
Mondays,
that's when they updated, so. I
Yeah.
haven't checked this week yet.
so Mondays and Thursdays are when they update. So there are currently about 102 students in quarantine. And, yeah, so 102 in quarantine, 20 isolated. Between Thursday and Sunday, there were 11 new student cases. So that is continuing to be high or possibly rising. So
Do you think it's likely that we'll go home after Thanksgiving?
I don't know. I know the governor is supposed to be providing some new guidelines today, especially for places where there are concentrations of 18 to 35-year-olds. So here we are. So whether that'll include universities, I don't know.
Yeah, the federal lockdown was Thursday, Friday?
Yeah,
It's
so.
on St. Thomas that just.
Mhm. Yeah. So Bethel had MDH come in and do saliva testing, just massive saliva testing. I think they tested over 800 people. About 700 were from their community, or from the Bethel campus. It was open to anybody. But I think as of so they did the testing on Wednesday last week, and by Friday, they'd had 77 people from their community report to them that they were positive from that test. So about 10% of the people they tested. So that's why they locked down. But yeah, so do make sure you're taking care of yourself. Make sure that you're doing all the things you should be doing. Stay home when you're not feeling well. If you've been in contact with somebody who's had COVID or who has COVID, take the time and quarantine. So, okay. And then, yeah, make sure that you're getting in touch with health services. So a couple ways to do that. There's the 5353 number on campus, and then there's the reporting form through the ROC. So either way, but we want to make sure that so the faster we can catch cases, the more we keep it from spreading and the more likely we are to stay. So we want to make sure that we're actually catching the cases that are present. So, okay. We should probably do some dynamics. Let's see here. Back to this. Okay, so last time we looked at, we were starting to look at instantaneous center of rotation. And so we had done a couple of examples, one of which was the cylinder rolling between a couple of plates. And so we wanted to know, so we said it had to roll without slipping. And so the speed, the tangential speed at the edges had to match what the plates were doing, which meant that our center wasn't stationary. It actually has a velocity to it. So that is what we did last time. We'll take a look at a different problem today. So for this one, we've got a block D that's moving at 3 meters per second to the right, and we want to know the angular velocities of the two links that are connected to it. So, where might we want to begin?
Listing our notes.
Listing what we know and what we don't know, always a good starting point. Okay, so what do we know here?
Velocity, velocity.
Okay, so we know the velocity of block D. What else is known?
The lengths of the two bars.
Okay, so we've got the lengths of the two bars. So they're both 0.4 meters. Okay, we've got our angles. With that, is there anything we know how it has to move?
We know A is not gonna move one day.
Okay, so VA has to be 0. What about BD? Do we know anything right now before we actually solve anything about directions of velocities?
We know it's translating and rotating.
Okay, so we know it's translating and rotating, but look at specific points on BD. So for point B, how does B have to move?
That's to kind of like open up this.
Okay. Think more about the point itself
Would
and less about the connection.
like move downwards, or like to the right as well.
Opposite eye
Hmm?
to move in opposite eye direction that they usually have.
Okay.
I was just about to say, it has angular velocity only.
Okay, so there's an angular velocity.
Angular velocities have to be the same. But like in opposite directions.
Not necessarily.
There's an angular velocity, and you have the radius of AB, so you can times the velocity of B, and that's also equal to the velocity of B on the DB.
Okay, so the velocity of B has to be the same on both lengths. How does it have to move if we just ignore all of BD? What does its velocity have to look like? What does the velocity of B have to look like?
Generally going towards the ground at an angle.
Okay.
Okay, I think we're on the right track, Titus. I think you actually did say it.
It's gonna move tangential to AB.
Okay, so it has to be tangential to AB. Because we're pinned at this end, AB is fully rotating about point A, which means the velocity at B has to be tangential to that. It has to be perpendicular to this, and it just so happens that this angle at this point is 90 degrees, which means the velocity of B is actually right along the BD direction. Okay. What do we know about the motion of D?
It's just a translation parallel from.
So it's translating, it's parallel to the ground, so it's an I hat. movement. Okay. Okay, and we know what that one is. We know that one's 3 meters per second. Okay, so now we also have some dimensions here. So we know this is 0.4 meters. Which way is BD rotating? Is it clockwise or counterclockwise? Has to be counterclockwise? Okay, that's the way that this works, so omega BD needs to be counterclockwise. Okay, so if you flip back a couple pages, how did we figure out where our instantaneous center of rotation is for this scenario? And which scenario is this? What do we think?
That second scenario,
Okay, which is what?
If we know the line of action of two non-parallel velocities
Okay.
at points A and B, we can draw lines perpendicular to each, and IC is at point that they intersect.
Okay, so we have non-parallel velocities of 2 different points. We can confirm this is pretty well not parallel velocities. And so we can we're going to draw lines perpendicular to each of those velocities from the point. And then where they intersect will be our instantaneous center. So we'll take this one and draw that way. And then this one's just straight up. All right, so got a right angle there and a right angle here. And then we know this angle is 45 degrees. So that one also has to be 45 degrees. And if we've got one angle that's 90, one that's 45, the one up here needs to be what? Also 45? Okay, so this point is our instantaneous center. And so then we've got a radius RB with respect to IC and RD with respect to IC. And so we should be able to solve for those just with some geometry. Okay, so if we've got a 45, 45, 90 triangle, and we know this side is 0.4 meters, what does that tell us about this side? Same? Okay, so our B with respect to IC has to be 0.4 meters. And then how about our D with respect to IC? Okay, so we can multiply by square roots of 2. We can also take 0.4 meters and divide by the cosine of 45 degrees. Or the sine of 45 degrees, either one works. And we should come up with a radius 0.566 meters for that angle. Okay, so now what is it that we're trying to find again? Okay, so we need angular velocity of AB and angular velocity of BD. Do we have the ability to find the angular velocity of BD with what we know at this point? Okay, so how would we do that? You agree to it, and then I'm gonna make you tell me how. So at this point, we know one velocity, right? So we need to work with D. What were you gonna say, Dylan?
Velocity equals omega times.
Okay, so our tangential velocity is equal to angular velocity times r. So here, VD needs to be equal to omega BD times RD with respect to IC. Okay. So then omega BD is equal to the velocity of point D divided by that radius. And that should give us 5.3 radians per second. And so that gets us our magnitude, and we need to write down magnitude and direction. So can either do a circle arrow with an arrow pointing in the right direction, or we could say CCW for counterclockwise. Either one's okay. We could also say positive Z, positive K hat. Okay, does this make sense so far?
Explain really quick how you figured out that it was counterclockwise.
So we had figured that out already. So we said in order for this point to be moving this way and that one to be moving this way, it's got to be rotating like that. So it wouldn't make sense to go the other way. Plus our instantaneous center is here. So once we've got our instantaneous center, we follow kind of what direction the arrows for velocity are going. So, okay. Okay, so now we know the angular velocity of one of our links. What can we do to get the other one?
We need to find another instantaneous center for the other car.
So remember, it's instantaneous center of zero velocity, and point A is not moving. So that is our center. But let's look back up here. What did we say has to be the same on both points? There is a point where they are joined.
Velocity of B.
So the velocity of B has to be the same on both points, otherwise things break. Okay, so as long as this linkage isn't breaking, velocity of B on BD has to be the same as velocity of B on AB. So what should we find? We should find velocity of B. Okay, so if we find velocity of B, what's that equal to? Or what's our formula? So omega BD,
B with respect to AC.
okay, our B with respect to IC. Okay, so we can do this, we can solve for VB, and then do the other equation for AB, or we can say VB is also equal to, what else?
Omega AB.
So omega AB times, okay, so RB with respect to A. And so since we know those things have to be equal to each other, we can just solve within that for the omega that we're looking for. So we're looking for omega AB. So if we solve for that, we have omega BD times RB with respect to IC divided by RB with respect to A. And in this case, those two R's are the same. That will not be the same in every problem. But in this case, it is. And so we have 5.3 radians per second times 0.4 meters divided by 0.4 meters. And so omega AB works out to be 5.3 radians per second. Now, what's our direction?
Clockwise.
This one has to be clockwise. Okay. So for B to have the velocity this way, about a point at A, it has to be, omega AB has to be clockwise. Okay, so we can write that either with the arrow, with CW, or negative K hat.
So is it okay to assume that if both the bars are the same length and are at the same angles, will they move the same angular velocity?
I would still want you to show that. But it would be reasonable to assume that they should be about the same. So when you check your work, that would be a good justification. But you should still show your work. Yes.
So say if the question was on the test, would you want us to prove or that both of them are the same?
I would want you to show everything we just did. And not just say these have to be the same. Because then I can't give you any points for actually showing your work. So. Okay. Any questions on this one? I'm hoping it's less scary than it maybe looked initially. Okay.
Once we got the like instantaneous center,
Mhm.
it made it a lot easier.
Yeah, so the main thing with this is looking for, is there anything that's just purely rotating? Then you know what the velocity has to be. Okay, so it's the same with that problem on the homework that had the wheel and the length to it. That point on the wheel had to have a tangential velocity. That was the only option. So if you knew that piece, and should have been able to work kind of from there. So yeah, that'll be, look for directions that you know what direction something has to move. Okay, so then just a little bit more with our rolling. So if we're given, maybe R, some sort of an alpha, and an omega, and maybe this is our center of gravity, and that's point A. Okay, so if we know our radius, our angular velocity, and our angular acceleration, we should be able to find the velocity and velocity and acceleration of the center of gravity. So essentially, if we're thinking about this like a wheel, how fast is the wheel spinning? And then how fast is the car moving? Okay. All right, so the key here is that we're rolling without slipping, which means our instantaneous center is A. So it's the point that's in contact with the ground.
We're not gonna have slipping on the test, right?
No.
Okay, thank you.
Okay, so
But at that very instant, velocity of A is zero.
at this very instant, velocity of A is 0. Next instant, it will not be. Which means acceleration at A has to be something that is not 0.
Are you saying that the acceleration is just all normal, just changing direction?
Not necessarily, no. So, in fact, if our formula for normal acceleration is v squared over r, point A has no normal acceleration. So point A has to have acceleration because it has to have acceleration, it has to have tangential acceleration because it is 0 for this instant and this instant only, and then it's going to continue with some sort of velocity. Okay. So just like when you throw a ball up in the air, it stops for a second, or for, a fraction of a second, but it has an acceleration the whole time.
But the thing I'm confused on is, doesn't A always have tangential velocity if it's on a wheel that's spinning?
So the key here is that it's a wheel that is rolling, not something that's spinning freely about its center axis. Okay, so that's what we'll get into why, but that's the key here, is that point A has 0 velocity, point G does not. Okay, so as our cylinder rolls, if we're starting with this, the line here is essentially the path of point A, and this one is the path of our center of gravity. Okay. So if we look at velocity of the center of gravity, we can find that as the velocity of point A plus omega crossed with r g with respect to A. Okay. So then at the instant that we're shown here, where A is in contact with the ground, Then you have VG equal to 0 plus, and VG should actually be VG I hat, right? Because it's going to be moving that way, plus omega. So what direction would our omega be if we're rolling here?
Okay.
So negative k, because we're rolling clockwise, and so we get a negative k. So we have omega in the negative k hat direction. We're crossing that with the position of G with respect to A. So that's going to be R in the positive J hat direction. Okay?
So it's positive J hat because to get from A to G, it's moving in positive Y direction.
Yep. Okay, so then we've essentially got a negative omega R, and then we have K hat crossed with J hat. So because it's the position of the position of G with respect to A. So to get from A to G, we go up. Okay, so we've got this negative sign that we're going to take care of here. We've got omega times R and then K hat crossed with J hat. So that should be a negative I hat. Okay, so then VG I hat is equal to omega R I hat. So we're used to using omega R as a tangential velocity, and it still functionally is, because we're rotating not about the center of the wheel, but about point A at this instant. So the point that's in contact with the ground is our instantaneous center, and so the whole wheel is functionally rotating around that point instead of rotating about its center. Okay, so then VG ends up being omega R, which is a tangential velocity. And we could find the velocity, if we found the velocity of the point opposite of A, then at this instant it would be 2 omega R. Also I hat, right?
Be 2 omega R?
Yep,
Oh, just because.
because it's 2R. Okay. Does this make sense? Okay. Okay, so VG then is omega R I hat, or positive omega R. So then we're also asked about the acceleration of point G. And let's see. Did I actually get into this? I actually got into this. No, we're going to get into it anyway. Okay, so the acceleration of point G is going to be equal to the acceleration of point A plus, we need to account for a tangential piece. So anytime we've got rotation, we need a tangential piece of our acceleration. which may be 0, but we should account for it anyway. Do we remember how we calculated tangential acceleration? I'll give you a hint, it's very, very similar to tangential velocity. Okay?
They're just angular acceleration times radius.
So we need angular acceleration crossed with our radius. Okay, when we have rotation, what's the other type of acceleration we get?
Translation.
No.
We have what?
When we have rotation, we have our tangential acceleration. What's our other acceleration?
Normal.
Radial or normal? Yep. And how did we calculate that? We had a couple different formulas for it. Those of you online can feel free to chime in too.
Would that be RV squared over R?
Close.
Omega squared R.
So we like to use the omega squared r version here, because it doesn't depend on the tangential velocity. So it actually turns out, so it's, if you remember, it's omega crossed with omega cross r. So we end up with a negative omega r squared omega squared r. And because it's in the negative r direction, we know it has to be a j hat component.
So the negative is just like the formula you use. That's not like, is that included with the j hat or?
Yep, so that's included with the j hat. So so it's in the r direction, but it has to end up being opposite of what r is up here.
So we're finding acceleration at g, and the normal acceleration is pointing down towards the center, and the center is at a. So that's why it's
Yes.
negative j.
Yep.
Okay.
Yep. Okay. So now we can actually split up our directions, so x and y. So if we look in the I hat direction and the j hat direction, which direction or directions does g have acceleration in?
I have,
So really just I hat.
yeah.
Okay.
For this,
Yep.
So that means we can use the equal 0, right?
There's some other things we may want to know. So we're going to say in the I hat direction, AG is going to have to be equal to, actually, let's see. So we should actually give this one a direction. So functionally, if we look at the path that we're taking here, point A is only really going to have an acceleration up. It's not going to have an acceleration backwards, it's going to just have an acceleration up. So this will be j hat. So we ignore that component. We didn't worry about our acceleration or our directions here, but alpha, we were told, had what direction?
Okay.
Okay. So this should be negative k hat. And r, we said, was a positive j hat. And so this should work out to be alpha r in the positive I hat direction, just like it worked out before.
Because if we just did positive k hat, j hat, it would be negative.
Right.
This one would be negative.
You end up with two negatives in that multiplication. Okay, so then the only component here that has an I hat is alpha rg with respect to A. And then we said G can't accelerate vertically. So this has to be 0 equal to A sub A minus omega squared r. And so the acceleration of point A is omega squared r. Okay. Okay. So, going to say something that I usually don't in this class. These apply to every situation where we have something rolling without slipping. So these equations apply. Okay. So very rarely tell you that it always is true. In this case, these are going to apply anytime we've got something rolling without slipping. As long as we're rolling on, one surface instead of between two or something like that. Okay. How are we doing at this point? We understand where this came from?
We don't have to like on homework problem and stuff, we're probably not gonna have to derive these, anything like this, right?
No, you could use these. Just make sure that it's an applicable scenario. Okay, so we'll jump over to the other packet. Okay, so we've looked a little bit at relative motion. We have considered what happens with velocity and acceleration, but up to this point, we've only dealt with reference frames that are translating. We haven't yet looked at systems where we can have rotation. So,
Was the wheel not that case then?
wheel was that case, but so the key is our reference frame, whether our reference frame is rotating or translating. So if we fix a reference frame to the center of a wheel, it won't change where it is. It can just translate.
So basically, that was different instead of at this instant. And that's why we did these equations we did.
Right, so it was an at this instant and we weren't really worried about, yeah, I guess we were referencing a point that was gonna change, but we were able to do everything in a fixed sort of reference frame. We're no longer going to be able to say that that's true. Okay, so we start out with this equation that's the same relative velocity equation we've dealt with since physics. And so if we take a derivative with respect to time, we're going to find relative acceleration of 2 points. And so we need to take a time derivative of VB with respect to t. Okay. So first one's easy. It's just a sub b. The second one is just a sub a. And then this one, we need acceleration of b with respect to a. And that's going to end up having a tangential component and a normal component. Okay, so if we're looking at an object, it's going to have some rotation as well as translation. The translation piece will be picked up easily by the same 2 points. But if it's rotating about some point on the object, we'll need to account for tangential and normal accelerations of 1 point on the object with respect to another point on the object. Okay. All right, so this tangential component is going to be perpendicular to RB with respect to A. So to that radius of point B relative to point A. And it has a magnitude alpha times RB with respect to A. So the angular acceleration of the object and the radius. So just like we've done before, this is a tangential acceleration of something that's rotating. And so we get alpha times R as that value. Okay. We're also going to have a normal component, and it's going to be in the direction of B to A. So not B from A, but B to A, with magnitude omega squared RB with respect to A. So this B to A is the opposite of R, B with respect to A. So that's the negative we had in the last problem. Okay. All right, and so if we write this out, we get acceleration of B is equal to acceleration of A plus alpha crossed with R minus omega squared RB with respect to A.
Is there a vector on the delta or the omega?
No, because it's a quantity squared. So we looked at this a couple classes ago, but functionally the negative omega squared r is coming from an omega crossed with omega cross r. And so if you work through that, you end up with just the opposite of the r direction. Okay, so put another way, or maybe a little more visually, if we have a path of A that looks maybe something like this, and a path of B that's maybe something like that, and let's say we've got an acceleration of A and an acceleration of B. We can break that down into pieces. So to get the acceleration of B, we've got the acceleration of A that we apply to both points. And then we have this R B with respect to A. Okay, and for these 2 points to have the directions of acceleration that they do, we have to have rotation this way, right? So we have to be going clockwise. So we're going to say omega and alpha are both that way. And so we're going to have an acceleration of B with respect to A in the normal direction, and a component in the tangential direction. And so that'll give us a net AB with respect to A that's somewhere in between them. Yep.
Could you zoom in a bit?
Yeah, sorry. Okay, so we've taken the 2 accelerations. We've said to have accelerations in the directions that they do, we have to have clockwise rotation. We can break this down into an acceleration of point A, a translational acceleration of point A applied to both points. And then we're adding to that the rotational components for that body to be rotating. So we have our tangential component and our normal component. And so then functionally we end up just adding all of those up. So
are we treating the acceleration of A as like the translational?
Yep.
And B causing the rotation? That kind of
It's not necessarily what's causing the rotation, but we're essentially saying A is the point that we're tracking, and we're fixing our internal or our moving reference frame to point A. So functionally, we're looking at having some sort of a little xy attached here. And then as this is rotating, that x and y stay with the same orientation relative to A, so they're going to rotate with everything else. Okay, so then to get to acceleration of point B, we start with our acceleration of point A, which is this way. And then we add to that, we're going to do tip to tail. So we can add to that our tangential acceleration, and that'll be whatever it is. And then our normal direction perpendicular to that. And then we look at what our net acceleration is from adding those up. And we get acceleration of B. Okay, so we're taking pieces of acceleration, we're adding them together from some pieces that we know. And then the idea here is that as long as we know alpha and omega, and we know the acceleration of A, we should be able to find the acceleration of any other point on that object, just by adding vectors. Okay?
Can you say that again?
So as long as we know what our rotation is, so we know alpha and omega, and we know an acceleration of point A, we should be able to find the acceleration of B anywhere B is on that object. So we can move, any point on that object we should be able to find an acceleration of. And functionally, this is the acceleration in kind of our global reference system. So in our fixed reference system, we can get to an AB. Okay. So I think we're going to skip the next page for now and go to the example. And we may or may not finish this, but we'll start it at least. Okay. So we have rod AB, and rod AB is going to move over a small wheel, while end A moves to the right with a constant velocity VA. So if end A is moving toward the right, where is the rod actually going to move, and how is it going to rotate? Okay, so point B is going to go higher, and we're going to be rotating counterclockwise as we go. Okay. So we're interested in finding the angular velocity and angular acceleration of point B, and then the components of, angular velocity, angular acceleration of AB, and then the components of VB. Okay, so with a problem like this, sometimes it's going to be easier to track a parameter that's going to track kind of one parameter that'll vary with motion, and use that instead of trying to just brute force solve everything. Okay. Is there a question online? Be unmuted. Maybe not. Maybe that's the heating system. Okay. All right. So I've got a couple things written down here. because the track, or the piece that we're going to track is theta. So we're going to track how this angle changes as we go. So we've got this XA that's going to be changing, right? So as A moves to the right, XA will be getting smaller. B is to the point where the wheel is, so that's going to stay the same. That'll be constant. But that means that theta is going to change, and it's going to change as XA gets shorter. Okay, do we see that? Okay. Is there some dissent there? Or are we okay?
Is E and B and I basically the only non-changing values?
Yeah, so this is actually supposed to be an L
Or should I say constants?
length. Yeah, so B and L are not going to change, they'll be constants.
Okay.
XA and theta will both be changing. Okay, so we know tangent, opposite over adjacent, so that's B over XA. But we can also do a cotangent, and so that's XA divided by B. And so we've got a quick note on what the formula for derivative of a cotangent is. But we're going to use U substitution to solve this initially, and then we'll substitute back to get to what we need. Okay. So essentially, if we're substituting this, we've got theta equal to the inverse cotangent of U.
Did I ask, why did we go from tangent to cotangent during your meeting?
Mostly because it's easier to track a numerator that's changing than a denominator that's changing. And the derivative of the inverse might be simpler. I haven't double checked that, but. Okay, so if we take a derivative of our theta here, with what we're given up at the top, we should end up with a negative U dot divided by 1 plus U squared. And then we can take a second derivative. And so we've already got our negative sign out front. But we've got to use quotient rule. Okay, so derivative of the top times the bottom. So 1 plus U squared times derivative of our top, which would be U double dot. Then we're going to subtract the top. So U dot times
2U. 2U.
So the derivative of, right, so this is just the fx part.
Yeah.
And then, yes, we need 2U U dot. And then we need our denominator squared. Okay, so if we simplify this, theta double dot is alpha. And so if we do a little bit of rearranging, we're going to take this term and move it up front. And so that'll be 2 u dot squared divided by 1 plus u squared quantity squared. And we're subtracting off. So here we can cancel one of our 1 plus u squareds. So we get u double dot divided by 1 plus u squared. How are we doing so far?
So it's not negative the first fraction plus the second fraction.
Right, because we had a negative and a negative. Okay. So if we substitute back, we said that u was going to be substituted for the cotangent of theta. So we essentially set u equal to xa divided by b. Okay, so then u is equal to xa divided by b, which means u dot needs to be xa dot divided by b. Remember, b is a constant, so xa is the only part that will have a derivative. So xa dot is va. And then u double dot will be xa, let's see. Right. No. Okay. So we'll go from VA, but this XA, we know it's moving to the right, which means we know XA is getting smaller, which means VA should be negative. Okay, so then we've got negative VA dot over B. So if we take a derivative of VA, what does that mean to be here?
Acceleration?
So it's acceleration, but
The board.
okay, sorry. So this will be an acceleration, but what were we told?
Constant velocity.
Constant velocity. So u double dot is 0. Because we're told VA is constant, so it has no time derivative. It has a 0 time derivative. Okay. All right, so then we can go ahead and look at some of these other pieces. So if we go back to our omega equation, that's a negative u dot. So we said that's negative VA over B divided by 1 plus u squared. So XA squared over B squared. Okay, and so if we multiply the top and the bottom by B squared, we'll end up with B squared VA divided by B cubed times 1, let's see, Yeah. 1 plus XA squared over B squared, or then I can, so we can cancel a little bit further. Get rid of one of those and that one. So this is going to simplify just a little bit more. Okay, and the reason that we know this has to be counterclockwise is because of the direction A is moving and the point it needs to be pivoting around. Okay, so we've got that one. Now, before we try and substitute back into our alpha equation, we should take a look at these and what we've got in terms of our terms here. So we have a u dot in our second term, or u double dot in our second term. We said that has to be 0. So that whole thing goes away. All right, and maybe we can just do this right here. So we have 2u, so xa over b, times u dot squared, that's negative va over b squared, divided by 1 plus u squared quantity squared. Okay, so we've got 3 b's we can move to the bottom. And then you need some foil with the other piece of it. Let's see. Actually, yeah, we're gonna multiply this by b over b. Add. So that makes this a b to the 4th. And then we've got 1 plus xa squared over b squared times 1 plus xa squared over b squared.
So there's 2 now? Or
Yep, because that whole quantity was squared. 1 plus u squared squared. So we can just multiply them like that. The reason I multiplied by b over b is so that we'd get a b to the 4th. And so then we can put a b squared in each of these. Okay, so let's maybe, I'm going to rewrite this on the other side of the page so that we've got a little more space to work. So what we came up with was alpha equal to 2b
Can't see it.
XA VA squared divided by B to the fourth times 1 plus XA squared over B squared times 1 plus XA squared over B squared. And so what I'm going to do is basically split up the B squareds. So the B to the fourth into a B squared and a B squared. So I can multiply each of those parentheses by B squared. And so if I distribute this in, we get a B squared plus XA squared over B squared times B squared. So this just becomes XA squared. Same thing here, B squared plus XA squared okay. And because we have to do the same, we've got the same rotation as we did before. So this is also going to be counterclockwise. Okay, so that looks messy, but essentially at any given time, if we know a constant XA, we know B is constant, or sorry, we know VA is a constant, we know B is a constant. So at any instance, if we know what XA is, we should be able to get to alpha. Okay. Okay.
Is that like for a bunch of problems, or like what can you apply those equations to?
You can apply that equation to this scenario.
Just this one?
Mm-hmm. But the approach you can apply more broadly. Okay. We were also asked to find x and y components of the velocity of v, but I think we're going to hold off on that and spend some time letting you ask some questions about the test. So, what would you like to know or review?
We did a problem in class, and it was like this. It was the one with the screw. There was a beam in the middle holding it.
Mm-hmm.
I have a question on one of those. We found that the angle of the resulting vector somehow. I don't really know how we did it.
Okay. Okay, so we had a problem that looked like this. And so this was looking at a square threaded screw. And so we had to use those friction equations. And the first thing we needed to do was to solve essentially the statics of our system here. So C is the collar that has threads, B is just resting. And so there'd be a normal force equal to its weight. to hold it there. And then we were looking at the collar, and so C is going to have a force applied down on it. And essentially, this tangent of theta was coming from, an equation that we had looked at.
Yeah, that was the triangle one, right?
Right.
H2.
Yep, so when we were looking at the square threaded screws, we had different scenarios where we had impending motion either up or down. And so that tangent was related to the pitch and the mean radius of the thread.
It was that second angle, it was the constant
Second
turning, I
angle.
didn't get that, but I don't understand it further.
Okay, so the B sub K? Okay, so that is really just coming from the definition of coefficients of friction. So when we're dealing with friction, if we've got, let's just say a box, and we've got a normal force, and we've got some sort of friction, and there's weight and a pushing force, that angle is coming from a resultant of F and N. So we have this resultant R that's going to be like that. And then, so the magnitude we'd find by Pythagorean theorem. And let's see, make sure I remember and do this correctly. Yeah, okay. So then the angle is coming in there. So it's the direction of that resultant force with respect to the normal. And so phi, or the tangent of phi, is equal to the opposite, or the friction force, divided by the normal force.
Oh, no, we'll cancel. That's because, yeah, because F equals normal times the coefficient constant, so the ends will cancel. And that's why it's equal to just the coefficient constant.
Yeah, so we could do that. So essentially that's going to work out to be mu.
Okay. Got it. Yeah, because I just saw that and like, I had no idea where it came from, so it makes a lot more sense.
Yeah. So that's our relationship between coefficient of friction and basically the relationship between our normal force and our friction force. If we were looking at it as a combined result. Good question. What else?
Let's choose like a math one for the next problem. It's like there's one that we started. Did you end up recording that one information or? Could be.
Probably not.
Uh-oh.
I don't know. Let's see. The one we started that I didn't get finished. Take a look at it. So I'm guessing, was it this one?
No.
This one? Those are the mass moment of inertia problems I've got.
This one might have just been like 2 notes on it, but anyway, I was going to the next problem.
What does it look like?
Yeah, it was that one, but I think it's just like internal notes that I think.
Oh, okay. Yeah, that was, I think, just notes that didn't actually get solved. So it was more looking at how we go about finding what our derivative of the volume is. So the idea being you can either look at it as kind of a difference in radius, sort of a like z times dr versus the area, or really this would be, let's see. dr, or pi r squared dz. So looking at which way do we do this, are we looking for kind of this portion and integrating out from 0 to r, or are we integrating?
And what method are you providing the properties of geometric shapes, the formulas?
Yeah, so I'll give you the tables that are in the book for common geometric shapes.
Like a soft copy?
I've seen I trust you guys to do that well. Last time. Also got students who are needing to take it virtually, so it probably format and have you get the problems and put in the answers there, and then do your work on paper and submit that like you would an assignment. Okay, so it'll be kind of 2 pieces that get submitted. But that way, everybody's got the exam in the same format and everybody can submit it. So I think that is what we'll do.
And then I have one more question. It was on a friction problem, and it was on one of the ones that you assigned us, or not? Or in the part B, and it was asking if there's 2 blocks sitting on top of each other. Bottom one was getting pulled out.
So block wedges.
No, it was just 2 blocks on top of each other. I mean, yeah, kind of would, but it was 1 block and 1 block.
Okay.
There's a tension holding the top rope, and to the right, it's like connected to a wall. Yeah.
Okay, so a rope connected to a wall.
And then the bottom block was feeling a force out to the left.
Okay.
Could you move the screen up a little bit? Okay, yeah, there's the part, that was part A, but part B was if it was connected to the bottom. And in your practice, like in the way that you solved it, you didn't include, like you included the friction on the bottom block.
Mm-hmm.
And I'm just confused, why wouldn't you include friction in this example in between those 2 blocks?
There should be, unless you were told it was frictionless.
Shouldn't you say every surface though? You say the friction on every surface.
Well, yeah, because I did the first one, it was like connected to a pulley and it's connected to both of them. And that one was like pretty easy, I thought. But the second one, like you just kind of did it as a whole and I didn't see the friction in between the 2 blocks. But It's on Moodle.
Is this on the fourth one?
This was a Connect problem.
I think the problem is the road, like all the roads are down, and the age is sitting on the age is not moving.
Oh, there's nothing connected to
I think
any?
it's just saying like all the roads are down,
Oh,
so then it's just kind of one big one.
no, then that makes sense.
I think I know this one. Oh,
It should be about how many layers are there.
one of the little ones where, yeah, you have your two blocks on top of each other. They both have a tension wrapped on fully. That's what I'm talking about.
No.
Tickets. Okay.
That may be one I have to follow up on. You said it was 130.
134, 8.134.
Okay. Yeah, I will try and follow up with that via probably Teams. One more quick thing I wanted to show before we leave. Let's see. A couple of problems. I'm recommending that you use MATLAB if you can. You can work in teams of up to 2 or 3. Okay? Your solution needs to be distinct from other people in the class. Your group needs to have a distinct solution from other people in the class. I don't want a group of, 8 deciding to submit one solution. So 2 or 3. There is a questionnaire here for you to tell me who you want to work with. So those of you who have not yet taken MATLAB, please find people who have. Hopefully they'll be able to do some of the coding and you'll be able to do some of the working through of equations. Okay, so there's discussion here of what I'm looking for. Essentially, you've got a couple of options. There's 2 problems to choose from. You can choose whichever one you want, and I've suggested a couple different approaches. But essentially, you're going to be looking at, based on the loading, based on the geometry, what forces do each of those members need to support. And then we'll be getting into a little bit of mechanics with, you're given an allowable stress. And so you'll use that to come up with what the area, the cross-sectional area of each of those members needs to be to keep that stress at 20 KSI or 135 megapascal, and then figure out how heavy your structure is going to be based on that. Okay? So we'll talk more about this later, but I wanted to make you aware that it's there. So you're welcome to start on that anytime.